before we get into anything with the tangent function, the secant, cosecant, which is where I want to go today, I think it's good to talk a little bit about maybe how your calculator is programmed. Because when I was in school, you know, we were just told, hey, use these functions on a calculator. They're spitting back numbers. They really don't understand where those numbers came from. But working with it for a while, you kind of figure out, you know, it's just the relationship of, you know, similar triangles, that kind of thing, or unit circle type things, with the sine, cosine, tangent, secant, cosecant, cotangent, and how those values are being created. So, for instance, if I look at that green point up there, the y value is 0.37, right? The angle down here is 21.8 degrees. So in maybe a geometry aspect, we can say that we know that every single triangle, every single right triangle has a 21.8014094,864 degree angle. The opposite side of that angle divided by the hypotenuse will always equate to 0.3713906764. Okay? Now, that being said, that's not something we really want to memorize, right? Like we memorize with a 30-degree angle, the opposite side divided by the hypotenuse is always going to be n divided by 2n, or 1 over 2. So how is our calculator getting these values back? How does it know all of these sine, cosine, tangent ratios? My hopes are that you understand, or that you realize that it's not programmed to say, you know, user puts in sine of 21, calculator go find in a chart where it's already been programmed at 21, spits back 0.3713. Okay, because then what happens when the user types in 21.1? Does it go to the chart and say, okay, what's the spit back? And then 21.111, okay? At some point, you start to realize, well, that would be an infinite number of possibilities that the user could type in. Does that make sense? And then there's no way that the calculator has been programmed with an infinite number of outputs that are just simply a chart or a set of ordered pairs that get spit back to you, okay? There has to be some other way the calculator is working. Okay, because we could, now this is a lot, but it's just still only a small fraction of the total number of inputs we could use. We could use all of those inputs there, okay, because those are the angle measurements. We put any one of those in for the sine or cosine, and it's going to spit back any of these numbers, okay? So if I put in cosine of 48.0267, that number, I'm going to get that one back. Okay, that's what my calculator does. If I type in sine of this one, it's going to give me the y value here back. Okay, what I hope you understand is that your calculator is not programmed with a table in the back somewhere that references your input as this number and then spits this back. Okay, because somebody would have created that table, and that table is going to have an infinite number of entries, and that's impossible to type in. Does that make sense? Okay, so where does our calculator come up with these values? All right, our calculator, and it's a concept or a topic that you guys will talk about in calculus, is most likely programmed with a function to provide back those values for sine and cosine. Okay, so somewhere in the programming it says, when user types the sine key, access this function, this y equals function, and plug in the number that they just typed in into that function and evaluate it, and then spit back that evaluated amount. Okay? Well, the easiest types of functions to program are polynomial functions. Okay? So we get to what we call in calculus we call them Taylor series. And you guys know that series are just lists of numbers that have a little bit of a pattern to them, and we add them or subtract them, right? Okay. We can add them all up, we subtract them, we can add and subtract. One of the series, just dealing with the sine function, one of the Taylor series that your calculator is probably programmed with is something like this. X minus x to the third divided by 3 factorial. Okay? All that is, guys, x minus x cubed over 6. So it's x minus 1/6 x cubed. If I type that in, that's all that is. Okay? That's a polynomial that we've dealt with in college algebra, right? Just a basic cubic function. Okay? Well, if I look at that, is that curve somewhat approximating the sine curve between maybe negative pi over 2 and positive pi over 2? Would you guys agree with that? Okay. I'm going to zoom in here. I mean, the red curve, now they are different, but it's a really, really far distance that I have to zoom in to where I start seeing a gap between those two things, right? Okay, so I zoom, I'm not going to keep zooming. Oops, too far. Okay, so they're really good approximations here between negative pi over 2 and pi over 2, but they're cruddy approximations over here at maybe like 5 pi over 2. So if I type in 5 pi over 2 for this function, g, we know for 5 pi over 2 for the sine function, we should get back 1. But if I type in 5 pi over 2 for the red function, I get that number back, right? Is this a pretty bad approximation for 1? Does that make sense, everybody? Okay. So in order to clean that up a little bit, we continue this series. And this series is going to look like this. It goes x to the 5th divided by 5 factorial. So it looks something like that. Did that approximation now kind of get a little bit, it's still ugly, okay, and it's not any better. It's actually further away. But as I keep moving out, this red curve is going to get better and better looking for more and more of the sine function. So let me do minus x to the 7th divided by 7 factorial plus then x to the 9th divided by 9 factorial. So we're oscillating back and forth between our odd, it's plus or minus, but we got odd powers divided by then that power factorial. Okay, minus then x to the 11th divided by 11 factorial. We'll go out to 15. And we keep going further and further. And your calculator is probably programmed with a function that goes out much further than 15. But we get something like that. Okay. Do you see now that we're getting a better approximation for 5 pi over 2? Go 1, or a few more, I guess. X to the 17th. 17. Okay. And now we see, that gets me to pretty close to 5 pi over 2. But if I zoom in, you see at 5 pi over 2, there's still a gap between those two curves, right? Okay. But is this a much better approximation? All right. So like I said, our calculator goes much further out than this 21. And you look at this denominator, very large denominator, okay? But x to the 21st, okay, whatever x is, that's going to be a huge number as well, right? So a huge number divided by a huge number, that's going to not be all that bad of a value here. But the more I go out, if I go 23, 25, 27, this number is going to get closer and closer to 1, and it'll eventually be 1. For instance, what is nice about this now, if I, instead of using 5 pi over 2, let's use 5 pi over 4, okay? 5 pi over 4, if I say g of 5 pi over 4, so that is sine of 5 pi over 4, gives me that number right there, right? If I do f of 5 pi over 4, pretty much the same number, isn't it? Out to this decimal place. So if I take c minus d, okay, that's kind of the you know, change to a decimal or a percentage, that's the percent error between those two. All right. And it's a very, very, very small amount of error. So it's a really, really good approximation. Does that make sense, everybody? All right. And like I said, you calculate the more terms that we put in that f function, the less that error is. Okay. So that's easier for a programmer to type into your calculator to program every time that somebody says the sign or hits the sign key. Instead of referencing the unit circle or some chart or table, it's referenced and said, okay, I'm going to input that value into this function, this x minus x to the third over 6 plus x to the fifth over 120, and it's going to evaluate inside that function, and then kick back to you what it evaluated, and that then is the approximation. But we're going to make the argument that we're using so many terms in that function that it's not really an approximation, it's the exact value for the sine or cosine. Okay? And for us, using the technology that we use, there's really no need to have, you know, I would assume that the function that we have right now up there is good enough for anything that we would do input-wise. Okay? It's a good enough approximation. The reason I think it's important to talk about that is the sine function. Does it go from negative infinity to positive infinity on the x-axis? So it should have input values of negative infinity and positive infinity, right? So my sine function, I should be able to type anything I want to into my sine function, give me an output, right? You know, for instance, if I type in that number there, it gives me an output, right? Okay. But eventually, so if that's the idea, I should be able to type anything in that I want. Let's see what that one does. Domain error. Well, that doesn't make sense, does it? Can it have a domain error if my inputs are anything that it wants to be? So my thought is that this is probably referencing that Taylor series, okay? And that Taylor series is blowing up because it's not enough terms to evaluate that very, very large number. Does that make sense, everyone? Okay. But theoretically, we should be able to type in anything that we want to for the sine or cosine and get an output back. And that output should always be between -1 and +1. Okay. But here we're seeing we chose something that didn't happen. That's something that you guys will kind of investigate and talk about in a calculus class. I don't know how much you get into. It's been a long time since I've taught Taylor series and stuff like that in calculus. Been a longer time since I took it. But let's say that's the sine. Let me try something here. Let's go V. Oh, seriously? All right, let me just type this in. Let's go x. That's 1 minus. Now I'm going to use even values. So what do you think that's going to give me? Any guesses? No guesses. We just did the sine. And that was with odd values. So now I'm going to do the even values as exponents and factorials. Yeah, it's going to eventually give me the cosine function, or an approximation for the cosine function. Okay, so that curve there, type in the cosine. See how the cosine kind of mimics it? Or it mimics the cosine? Okay. Now I know it's getting kind of messy. So those are that's the Taylor series for the cosine, and that's the cosine. Is that all right, everybody? So that's probably what your calculator is programmed with there for the cosine. We know if I take those two things right there, which the top one, f of x, is sine. H of x, the bottom one, is cosine. If I divide those, so I take those two functions, I divide those, what's that curve start to look like? Tangent. So the tangent is probably programmed with something that looks like that thing there. Okay? It's pretty ugly, but it's a lot easier to program that than it is to type in an infinite number of input values and then an infinite number of things that the user could type in, and then pair that with the infinite number of outputs. Okay. We can also do, you know, 1 over sine. What's 1 over sine going to give me? Cosecant. So there's I get the cosecant programmed in. I can do 1 over cosine, and that would give me the secant, right? So that's, I was always interested and I was concerned about, you know, how is my calculator doing this? Because I know I can put in anything I want to as an x value or a theta value into my calculator, and it usually spits something back. Is it programmed with all those infinite values? No. And usually your calculator, guys, whenever you're referencing something like that, not necessarily just dealing with trigonometry, but when you're referencing something that has a potential number of infinite inputs to provide then infinite outputs, there has to be some type of function being used to do that, all right? Just because of the logistics of dealing with infinity. All right, so let's deal with the tangent function. So that obviously I'm not going to make you guys ever know that. Okay, next year maybe you will. All right, but I think it's a good thing to see and kind of maybe grasp, understand a little bit, just general knowledge type thing. Let's go to the tangent function. What I want you guys to understand is the creation of the tangent function comes solely from looking at that function there, and we're going to graph that one here in a moment. In that function there. If we know what those two look like as parent functions, we should have absolutely no problem graphing the tangent function. Okay, so I'm going to, and I think this is something that you guys need to be able to do, because I'm going to ask you next week. I know I told you earlier this week, or it might have been last week, that you're going to have some quizzes this week. That because of the 2-hour delay schedules, didn't really get through as much as I wanted to provide those quizzes, but they will be coming. Huh? There will be, so I will give you, you know, these graphs here. Ask you guys the sine, the cosine, might be the tangent. I might do some transformation stuff with those. Ask you maybe to evaluate some things. Just to see, I mean, it's going to be to see what you know about everything we've talked about so far with these curves in Chapter 6. I would be prepared for everything out of Chapter 6. So sine function starts at 0, 0, ends at 2 pi 0, halfway in between, we get pi. And then if those are our maximums and minimums of 1, we're going to get try to do a smooth curve here. Okay, so that's the sine function, right? Should be able to do the same thing for the cosine. The cosine starts at a height of 1, finishes at a height of -1, or not, sorry, reaches a height of -1 at some point. It starts at height of 1, finishes at height of 1. Halfway in between, that's the one where it gets to -1. And at those spots, we're at x-intercepts. Okay, that's something I think you guys need, you know, to go home and graph these things over and over and over again. Sit in study hall and graph them several times, because that set of parent functions right there is the foundation for graphing the tangent, the foundation for graphing the secant, it's the foundation for graphing the cosecant, and eventually the cotangent. Okay, so please, 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 please know what those look like, because on quizzes and tests, if you forget what the tangent function looks like, or maybe where the asymptotes of the tangent function go, this is going to be kind of your lifesaver for that, okay? So I'm going to just move some stuff around here a little bit. That's the cosine. Put there. Just kind of want to provide you what we're going to do, how we create the tangent function then from that information, okay? So this is going to graph over here as y equals the tangent of x, okay? When we do this, we're looking at these ordered pairs, okay? So the ordered pair of that point there and that point there. They both have the exact same x value, right? X value of 0. But their y values are different, okay? When we come up with the tangent function, we're going to use the exact same x value that those two things have. So x value is 0. But then we're going to divide their y values in the order of sine divided by cosine, because that's what tangent is, right? Okay? So if you remember, when we graph the sine function, the cosine function, the x's were always radians, okay? And then the y values were either y's off the unit circle or x's off the unit circle, okay? So when we complete the division of these y values, we are actually finding the tangent value at 0, okay? So what is, this is a y value of 0, this is a y value of 1, that quotient gives me what? 0. So at 0, 0 for the tangent function. That is an ordered pair, okay? Now I'm going to go to this point here and that point there, okay? They have the same pi over 2, right? So on the tangent function right now, I'd be looking at pi over 2 as the x value, okay? Now what is this y value? 1. What is this y value? 0. What's 1 divided by 0? Undefined. So for the tangent, what's that produce over here? An asymptote. Okay, so that's maybe help for you if you forget where your first asymptote for the tangent function occurs. That's the procedure of getting it, okay, or one of the procedures for getting it. If I'm at pi, that y value is 0, that y value is -1. What does that give me? Give me 0, okay? So I think maybe I got to move some stuff over here. Ooh. All right, so pi would have been, what, 1, 2, 3, 4, 1, 2, 3, 4. So pi is there, and now we got a point, another point at 0, right? So pi comes 0. Now if I look at that point there and that point there, at 3 pi over 2 being the x value, I've got -1 divided by 0, and that means that is undefined, right? 1, 2, 3, 4. So this would be 3 pi over 2 for me. And we have another asymptote. Okay. Now the tangent function is going to occur, one complete cycle occurs between any two asymptotes. Okay. So right now, what is that distance right there? Pi. So what is going to be the distance between that red asymptote on the right-hand side and the first asymptote over here? Pi. So does it make sense then that 1, 2, 3, 4, -pi over 2 would be another asymptote? Okay. I always think it's a good idea to draw in your asymptotes before you do anything else with the tangent function, because they're kind of your boundaries, right? Now, again, not only is it because that was pi, that interval was pi, so this interval has to be pi to find this asymptote, but if I went this direction, -pi over 2 units, that would be a height of -1. Negative pi over 2 units that way, that would be a height of 0, right? What's -1 divided by 0? Undefined. Okay. Now, there are some other points in here that we need to find, okay? And they're essentially that halfway point right there between 0 and pi over 2. That's pi over 4, correct? What would be the sine value for pi over 4? What's that y value right there? Root 2 over 2. At pi over 4, on the cosine, what's that y value? Root 2 over 2. What's root 2 over 2 divided by root 2 over 2? 1. So at pi over 4, you have a height of 1. So let that be 1. At negative pi over 4, okay, negative pi over 4, so that'd be right here. That's going to be negative radical 2 over 2. And that's going to be positive radical 2 over 2, right? So what's a negative divided by positive? A negative. So there would be -1. And those are the 3 points that are essential for us for graphing the tangent function. But it's 5 things total if we incorporate knowing the locations of the asymptotes. We'll connect those with a smooth curve. And then over here, so my hopes are that you guys see that little interval right there and that little interval right there. They are half of the period, right? Okay. And inside those intervals, halfway inside those little blue and green intervals, you reach your value of 1 and your value of -1 respectively, right? Okay. So over here, halfway between this little interval here, because that's going to mimic, oh, not the green one. That's going to mimic the green one right there, right? So halfway in between there, where am I going to be? What's my y value going to be? -1. And then halfway in between this one, my y value is going to be 1. And we can, kind of a cut and paste idea, but we can continue to get those tangent curves in those successive periods. Okay? All right. Yesterday, I kind of ended class with this, and you guys, the bell rang, you guys had to leave. So I finished the PowerPoint, or not the PowerPoint, but the presentation. But I think just so everybody sees this, I'll talk about it here. If I have tangent of bx, okay, and I just create this slider of b, so b can be anything it wants to be. And we know that when b is 1, okay, that's our parent function. That's the one we just graphed. So that gives us x equals pi over 2 as an asymptote. It gives us x equals pi over 2 plus pi as an asymptote, plus pi again as an asymptote. Does that make sense? So we have all those abilities of finding our asymptotes by finding the first one and then adding our period to that one. Does that make sense? Okay. But what happens when b changes? What happens when b goes to like 2? Okay, we know it gets compressed horizontally because that's what that transformation does. Okay, doubles the input value before we run it through the tangent. Okay, or if our b value is 0.2, it's going to stretch it horizontally. I want us to have the ability to find these asymptotes pretty quickly. Okay, because I think finding those asymptotes quickly is going to allow you to develop your graph a lot quicker. Does that make sense? Because that when I graph my asymptotes, I'm doing that because I know my curve is going to be inside those. It sets up those boundaries. So those would be the first things I'm trying to look for. So we know if I just look at tangent of x, we just said one asymptote. The first asymptote started at pi over 2, right? I then needed to add my period to that, so I added pi. Okay, but then I kept adding pi to find my next and next and next and next asymptotes, right? Okay, well, what's another way that you could rewrite that? Say it again. N times pi. That's perfectly fine. N times pi. So I have pi over 2 plus pi times n, okay? But n cannot be like 1.5 or 5/2 or 2/3. We want n to be an integer. Does that make sense? Okay. So that's going to give me, if I type this formula in, let's say x equals pi over 2 plus pi times n. It's going to ask me to create a slider for n. I want that. But n, like I said, it has to be an integer. So let's go from negative 10 to 10. And we'll go by increments of 1. All right, so if n is 0, this thing's wiped away, and we get our pi over 2, right? And that's where that asymptote is. If n is 1, okay, now we have pi over 2 plus pi, which would give me this second asymptote, right? And you can see then, as n starts to increase, are those always going to be asymptote spots? Okay? When n is 0, it gives me that one. When n is negative 1, it gives me that one. Pi over 2 minus pi would be negative pi over 2, right? And that's the asymptote that we're getting there at negative pi over 2. Okay? Well, is that the same then? Is that an asymptote when b changes? Is it an asymptote now? No. So we got to adjust our formula for that when b changes. And if I change b to 2, okay, we actually see that our asymptote is kind of bisecting this tangent curve, right? So it's right at that midpoint of that curve, or middle point. So how do we adjust this? Well, our first asymptote here, it looks like it happens at pi over 4, right? Okay, so this needs to be pi over 4. Okay, is that pi over 2 times 2? Is that still pi over 4? Okay. What if this was a 3? Okay. Now my axes are not set up this way, but if I write x equals pi over 6, does that look like the asymptote when it's 3? So I need my first asymptote to show up at pi over 6. So this would have to be a 3. Does that make sense, everybody? Okay. So this little number right here has to be the same thing as that number right there, which is our b value, right? Okay. So pi over 2b is actually going to give you that first asymptote. Okay. Then I want to add my period to that. Let me just clean everything up here. I want to add the period to that. So I've got pi over 2b so far. It's not a b. I'm going to add to it my period. Well, what is my period if I've got my period for my tangent is always pi. But if that's a number other than 1, it's got to be pi divided by that number, right? So pi divided by b. And I'm going to do the exact same thing. That's only going to give me the second asymptote. I need to put an n on that, where n is an integer, to get all my other asymptotes. Okay? So now if I reposition this, or rewrite this, this was pi over 2, pi over 2, but now it's b, 2b, so multiplied by b. Order of operations says I need that in parentheses first. Plus then pi over b times n, and I don't know what that g right there is, so we'll just delete it. Hit OK. And let's see if, when I move this, does it give me those necessary asymptotes? All right. And what's nice, okay, b changes, so let's stretch b out. So it's now tangent 0.4. Are those the right asymptotes for tangent of 0.4? Right? So this formula right here is something that you guys might want to commit to memory, because it's useful in determining where your first handful of asymptotes need to be. And when you're evaluating them, if you're trying to find their locations, obviously you let your b value be whatever it is in the function that you're provided with. And then you let n be 0, let it be 1, let it be -1, and that's going to give you enough of your first initial asymptotes to get what your tangent curve is going to look like. Okay? I know you're sitting there thinking, man, this is a lot of stuff. This is some work, and that's just the nature of the beast, guys. This is kind of the simplest way in the 8, 9, 10 years that I've been teaching this. The simplest way that I could present it to you, and hopefully you learn it that way. Okay. Giving you maybe different approaches, different techniques, maybe. Obviously, you could do something like this with graphing the tangent function, and if I wanted to graph like tangent of 2x, I could look at what does sine of 2x look like, what does cosine of 2x look like, and I could graph those, and then divide their y values to get my tangent. But it's very important to understand what those three parent functions look like. Is that okay with everyone? Okay. Now, division by 0 provided asymptotes. Okay. Division by 0 always provides asymptotes. So let's talk about another function that might happen in. If I look at let's just say, let me just kind of mess around my axes here real quick. Awesome, that undid everything I wanted to do. Oh well, all right. I'm going to look at the sine function. Sine of x looks like that, right? Okay, what is the reciprocal of sine? Cosecant, okay? So we're probably going to have time today to look at cosecant, but the same exact procedure would happen for cosine and secant, okay? So the cosecant of x, if I wanted to graph that thing, it's simply 1 over sine of x, right? And I want you guys to know that every single point that I put on here, okay, that point A, I'm going to change the rounding so it's, that point right there is some x value, comma, the sine of that x value, right? That's what every one of those ordered pairs y is doing. Every ordered pair of A, the y value is the sine off the unit circle, right? Does that make sense, everybody? So we call this curve the sine curve. So if I want to come up with what the reciprocal of this function looks like, can't I say that if I look at ordered pair of A, okay, I'm going to create another point. It's called B. And I'm going to let it have the exact same x value that A has. But instead of letting it have 0.47, because if I let it be 0.47, obviously, it's just that one, right? Okay. I'm not sure why it's putting a line in here. Because he used capital letter. That's stupid. X equals, what was it? X, comma, 0.47. Okay. If B. Okay. So you see at that point, obviously it's the same thing, right? So I'm using the same exact x value, but I don't, to get the cosecant, I don't want to use the exact same y value because that's going to give me the sine again, right? So what does the y value have to be? It has to be 1 over 0.47, doesn't it? Okay. So what I'm going to do is I'm going to write 1 over the y value of a, which is the 0.47, and see what that does for me. And it gives me that. Okay? And that ends up being the reciprocal of the sine at that x value of 0.49. For instance, if I was able to get this 0.49, see if I get to go to 0.5, what's the reciprocal of 0.5? It's 2, isn't it? Now there's rounding occurring, that's why it's giving me 2.1. Not exactly at 0.5, but close enough. So you see at that point up here would be at 2 if I was right at 0.5. Does that make sense, everybody? Okay. What if my a value was at pi over 2 comma 1? What's the reciprocal of 1? 1, right? What if I'm over here, again, at a y value of, let's see here, 0.5 for, it's close enough, 0.5 for the sine function. What's my y value go for the cosecant? 2, okay? So what I'm going to do here is I'm going to trace out. So that b value is all the ordered pairs for your cosecant. Does that make sense, everybody? I'm going to trace that point, see what happens. What's going to happen right here, though? Because that y value of a is 0, right? 0 over 1, right? Or 0 over any number you want it to be. But that number divided by 0 then cannot be done, right? So we get undefined there. So graphically, what should exist right here? An asymptote, okay? If I ask this thing to trace b, as I move a, that curve right there is half a period of the cosecant. There's your other half. Okay, so I'll zoom out here a little bit so you can see it a little bit better. Okay, so there's your cosecant function. All right, but it's just found by taking the reciprocal of your sine function, which is essentially taking the y values of the sine curve and you plotting those reciprocals against the same x value. Okay. If I just type in, just to clean things up a little bit, cosecant of x, zoom in, okay? What do you notice about some key points here? Well, you told me that you had an asymptote x equals 0, right? Asymptote at x equals 0. Where else do you think you'd have an asymptote on here? Any guesses? Pi. Where else? 2 pi. What are you seeing? Those asymptotes exist where for the sine function? What are they passing through on the sine function? Yeah, that point right there is an x-intercept for the sine function, isn't it? Okay. And mathematically, it's because the sine function, the y values at x-intercept are 0, right? And we find the reciprocal of 0, it's undefined. Okay, it does not exist. So that's why we get asymptotes there. So when you guys want to graph the cosecant function, the first thing is to actually graph the sine function. That's going to be a very useful thing for you because it automatically, if you know where the x-intercepts are for your sine function, you then know where to put your asymptotes for the cosecant, right? This value here, where my cursor was, that sine value was 1, right? What's the reciprocal of 1? 1. Is that an easy value to kind of determine? Yeah. Look down here at this point here. What's that y value? -1. What's the reciprocal of -1? -1. Is that kind of easy to graph? Okay, so let's talk about what the process is for you guys graphing by hand the cosecant. First thing you're going to do, whatever, and you do the same exact thing with transformations. But we know that we're interested in the cosecant of x, okay? What I suggest you do is graph on the same exact set of axes. It's reciprocal. So the reciprocal is sine, right? So I'm always going to graph the sine function. So, because that's easy, right? Or should be easy maybe at this stage. We're getting easier in regards to maybe graphing the cosecant. Pi over 2, 3 pi over 2. So we've got that, and that as points. So we got that there, and that there. So there's our sine function, right? And when I graph that, in the efforts of graphing my cosecant, I just lightly sketch it. I don't push real hard with my pencil because I don't want it to confuse me of what I'm really trying to graph here. Okay? But the reason I do that, the reason I graph my sine function, is because I know now, because of what we just kind of demonstrated, that there's division by 0 there, there's division by 0 there, and there's division by 0 there for the cosecant, right? So I put in it allows me finding that, allows me to find my asymptotes. But it also finds that value of 1, which its asymptote, or sorry, not its reciprocal is 1 as well. So that should be a point for my cosecant. And if my cosecant is going to have this value of 1 and it's going to move to the right, okay, the only way it can move to the right is if it starts to go up towards those asymptotes, right? Because if it moved down, we would have other x-intercepts and stuff like that, and we don't. If I move to the left, doesn't it go up? That's terrible, but you get the idea. And then at this point here, as I move to the left, it's got to go down. That's worse. Okay? And as I move to the right, it's going to go down as well. So that is one period then of the cosecant. Because after that, you're going to have that u that goes up, right? It's concave up. And you'll have another u that's concave down. So that's how you develop the cosecant. Okay? Draw in the sine function first. Find the asymptotes by using x-intercepts of the sine function. And then find your maximum minimums of the cosecant by using the maximum minimums of the sine function. Okay? The cosecant is attached to the sine. The secant is going to attach to the cosine. So if I wanted to graph the secant, I do the exact same thing, but I start off with the cosine. All right? Yeah. Monday, we'll start with this again, so you can see it one more time, but then we'll talk about the cotangent. Have a good day. Thank you. You too.